Hi, we would like to show you guys what we have understood about the Runge method. Before we go any further than this, I would like to state the objectives of this project, which is to enhance our knowledge about the Runge method and how to confront and solve ordinary differential equations, which is the ODE, and eigenvalue problems. Other than that, this method introduces another way to solve any particular problems. First, let us get to know more about this historical background of the Runge methods. According to the History of Runge methods by J.C. Butcher, the founder for these methods is C. Runge, and his work was published in 1895, which is the extended approximation method of the Euler to a more elaborate scheme, which was capable of greater accuracy.
Now I would like to introduce to you about the Runge-Kutta method. It is a fourth-order approximations. The initial conditions of it is x equal to x0 and y equals to y0. The ordinary differential equations is dy over dx equals to functions of f, x and y, while the recurrence formula is yn plus 1 equals to yn plus h times with t4, which is functions of x and yn and h. t4, xn, yn and h is called an increment functions, and the value of yn plus 1 depends on the value of the xn plus 1. This is the formula for the fourth order Runge-Kutta method, where is yi plus 1 equals to yi plus 1 over 6 times with k1 plus 2k2 plus 2k3 plus k4, whereas k1 equals to functions of x and y, and k2 equals to functions of x plus h over 2, y plus h over 2 times with k1, and k3 equals to functions of x plus h over 2 and y plus h over 2 times with k2, and k4 equals to functions of x plus h and y plus h times with k3. As the second order approximates, there are an infinite number of equations. Next, we are going to try some of the example for this fourth order. Given the ordinary differential equation is dy over dx equal to 3x squared y. The initial condition is x0 equals to 1 and y0 equals to 2. The step size used is h equals to 0.1, and the recurrence formula is y1 equals to y0 plus with h multiple with t4, which is functions of x0, y0 and h. Then we substitute the initial conditions and step size into our recurrence formula, whereas y1 equals to 2 plus 0.1 over 6 and multiple with k1 plus 2k2 plus 2k3 plus k4, y0 and h. For k1 equals to functions of x0 and y0, which is 3x0 square multiple with y0, and we substitute the initial conditions into our formula, we get 3 1 square multiple with 2, and the answer is 6. For k2, which is functions of x0 plus h2, y0 plus h2 or multiple with k1, and we substitute the initial conditions, we get 1 plus 0.1 over 2 and 2 plus 0.1 over 2 multiple with 6. Next, we will get the value of functions 1.05 and 2.3. We substitute into our formula, which is 3 multiple with 1.05 square multiple with 2.3, and the answer is 2.607. For k3, which is the function of x0 plus h over 2 and y0 plus h over 2 multiple with k2, and we substitute the initial conditions and the value of K2 into our functions, we get 1 plus 0.1 over 2, 2 plus 0.1 over 2 multiplied with K2, which is 2.607, and we get 1.05 and 2.38. We substitute the value into our formula. 3 times with 1.05 square multiplied with 2.38, and the answer is 2.872. Next, for K4, which is the function of x0 plus h and y0 plus h multiplied with K3. We substitute the initial conditions and K3 into functions, and we get 1 plus 0.1 and 2 plus 0.1 multiplied with K3. And we will get the value of function is 1.10 and 2 plus 0.1 multiplied with 2.872, and we get 1.10 and 2.287. We substitute the value into our formula. We get 3 multiplied with 1.10 square multiplied with 2.287, and the answer is 10.117. Once we have these 4 values, calculate value of y1, which is y1 equals to y0 plus h over 6 multiplied with k1 plus 2k2 plus 2k3 plus k4, y0 and h. Then we substitute all the value into our formula, which is y1 equals to 2 plus 0.1 over 6 multiplied with 6 plus 2 times 2.670 plus with 2 times 2.872 plus with 10.117, and we will get value of y1 equals to 2.278 and x1 equals to 1.10. It is much more accurate than Euler method calculation, which is y2 equals to y1 plus h times with t4, which is functions of x1 and y1, and the value of k1 equals to functions of y1, x1 and y1.
Now let us look at the example to solve the problem in general engineering by using Runge method. A ball at 1200 K is allowed to cool down in air at an ambient temperature of 300 K, assuming heat is lost only due to radiation. The differential equation for the temperature of the ball is given by d theta over dt is equal to negative 2.2067 times with exponent negative 12 times with theta to the power 4 minus 81 exponent 8, and the theta initial condition for theta is given by 1200 K, where theta is in K and T in seconds. Find the temperature at T equal to 480 seconds using Runge fourth order method. Assume a step size of h is equal to 240 seconds. Power 4 minus 81 to the power of 8. The recurrence formula for this question is equal to theta I plus 1 over 6 times with k1 plus 2k2 plus 2k3 plus k4 times with the step size, which is the h. For I equal to 0, t naught equal to 0, and the theta naught is equal to 1200 K, and this is the initial condition for this situation. The k1 is equal to f in the bracket t naught times t naught with theta naught. After we substitute all the value, we get the value for k1 is equal to negative 4.5579, and it is the same for k2. After we substitute all the value inside this equation, we get negative 0.38347, and also for the k3, and same is k4. For theta 1 is equal to theta naught plus 1 over 6 times with k1 plus 2k2 plus 2k3 plus k4 times with the step size. After substituting all the values inside this equation, we will get 675.65 K. And theta 1 is the approximate temperature at T is equal to T1.
which is equal to T0 plus the step size. And we get that T is equal to 240, while the theta 1 is equal to the approximate to the 675.65 K. For the next value of I, which is 1, and the T1 is equal to 240, and the theta 1 is equal to 675.65 K, which is all the values are from the previous calculation. And after we substitute all of the values inside the equation for K1, K2, and K3, and also K4, we will get K1 is equal to negative 0.44199, K2 is equal to negative 0.31372, K3 is equal to negative 0.34775, and lastly the K4 will get negative 0.25351. The theta 2 after calculate is 594.91 K. Theta 2 is the approximate temperature at T is equal to T2, which is equal to T1 plus H, and we get 480. And theta 2 is equal to the 594.91 K, which is the approximation.